All right, well, good noon to everyone. Welcome to Lecture 10. Today we're going to talk about generalized circuit elements and semiconductors, but first a few announcements as usual. So homework number 4, that's going to be online soon. That's almost ready, if not already online. Your lab number 2, and so there's a bunch of logistics with labs and that sort of things that may be confusing as to when they're due. Lab number 2 pre-lab is due next week. So it would be, oops, why did this come up here? So lab number 2 pre-lab is due next week. I guess it should, yeah, let's make it due next week during your lab session, although we could ask your TAs how you're doing with that. Yeah, let me not change anything just yet. We could talk about that. Lab number 1, though, the experimental part is due the week of 9/28. That's the Monday of the week, so that's a ways from now. The lab number 2 experimental part is due the week of October 5th, and so that's pretty far away there for you to be doing all of these things here. So it's mainly the lab number 2 pre-lab that's going to be due soon, which should be due in your lab next week. And so that means not the experimental parts, but just the pre-lab parts. This lecture, just for those who are not here, this is being done at 12 noon rather than our usual 2 to 3 p.m. But I am recording this and it'll be up on the course website as usual. Next week, unfortunately, I guess there's even more disruption to when our lecture occurs. It's going to be inverted to this week pretty much, where Monday and Tuesday cannot be at the lecture time. So what's happening next week is there's a big research meeting and I have to MC the whole thing. So I have to be there the whole time, and I cannot be there during class time. But I have time available early morning, so I'm saying Monday and Tuesday, the lecture will be 9 a.m. And that might even change to 8 a.m. depending on the meetings that come right after that. I'm sure all of you would love to wake up at that time in the morning. Maybe a lot of you already do. But if you do, you're in luck because that's when the lecture is going to be. Right now I'm going to say 9 a.m. But what I'm going to do is I'm going to change your Zoom links to the times that I can actually do it there. I will record these, of course, so if you can't make those times, then you'll still be able to see the lectures. I'll also need to miss the Monday office hours, but I will make Wednesday office hours, so at least I could do that. Yeah, like I said, I'll update the Zoom invites. Friday, though, 9:25, that will be the usual lecture time from 2 to 3 p.m. And again, all lectures are recorded, so those who cannot make the special times, you'll miss nothing as long as you go back and watch those lectures. Any questions about these announcements and logistics? There's a lot of them, so any questions? You can use the chat or just say something.
Oh, hi, Professor. Just wanted to confirm. So, there will be no Wednesday 2 p.m. lecture, but it's going to be moved to Tuesday 9 a.m.
Ooh. You are absolutely right. I screwed that up. I meant to say Monday and Wednesday. I don't know why I wrote Tuesday, and I even said Tuesday when I was reading this. Thank you for pointing that out. You would have seen that, I suppose, anyway on your Zoom link, because it would have come up on Wednesday. But yeah, it will be Monday and Wednesday at 9 a.m. Thank you very much for that. That would have been disastrous if you hadn't said anything. Any other questions about this? Okay. All right. So our lecture topics today, we will talk about generalized circuit elements. So that basically means how to model nonlinear elements, or what is a nonlinear element, because what we're going to do is model that. We'll start talking about materials and semiconductors. And so this is where we're going to pivot from sort of op-amp circuits and that sort of thing to physics and device physics. So we need to study the devices that we're going to use to make the op-amp. And those devices are going to be things like transistors and diodes that are based on semiconductor materials. So to explain semiconductors, it's good to first explain conductors and insulators, or at least remind you of what they are, and then see how they relate to semiconductors. Then I'll talk about doping, which is an important thing you can do to a semiconductor to make it conductive. But before any of this, let me finish up with what we were doing last time, which was bias currents. And I didn't quite finish that. We're almost done with that, but just to review some of this, we're talking about input bias currents here, and this is one of the 9 idealities of op-amps. This is a non-ideality where your op-amp, which is supposed to have no current going into the minus and plus terminals, actually has some current there. And that's caused by the physics of the devices that are making up the op-amp. That's something that we'll start talking about in this lecture. But the way we model them is just through some current sources that are going down because we want to model that current going into each of these terminals here. And I can call these current sources IB1 and IB2, but usually what a lot of people do is break them up into an average current, which is just exactly the definition of the average. So IB is equal to IB1 plus IB2 over 2. And so I can represent the average current here, and then I can represent an offset current, which is a difference or differential value. So IOS is just IB1 minus IB2 here. And so if I define IB and IOS, then IB1 equals IB plus IOS over 2. IB2 is IB minus IOS over 2. And this is just convention. This is the way that people like to do these problems. And what do I mean by these problems? Well, I'm going to give you a demonstration in just a second here. But you'll especially use these things in 140 and 240 later on to handle understanding of how these offsets get generated. And so last time we started doing an example to try to get you familiar with these offset currents and bias currents and how to work with them. So we took the example of a non-inverting amplifier. So just your regular R1 and R2 in feedback, and your input's supposed to go here. We're putting 0 as our input because we expect our output to be 0, but because of these bias currents, as we did the analysis last time, the output is not 0. Suppose, though, we wanted that output to be 0 no matter what, even if we had these output currents. Well, I said last time that one way that we can get that, or at least try to reduce this effect, is to add one more resistor to the positive input. And so here's where we're going to add that resistor. So we have R1 and R2, which are the main resistors in feedback, but then we're going to stick an R3 here, right at the input to the positive terminal. And right, that R3 in most circuits you'll think is not doing anything. In an ideal op-amp circuit, it's not really going to do anything here. But in this circuit, it actually does something. And what it does is, because it's a non-ideal op-amp, I've got these currents going in. This current IB2, it can't go into the positive terminal because this op-amp is ideal, and we're representing the non-ideality just by these current sources here. So that current can't go into the positive terminal, and so what it will do is go into R3. And if it goes into R3 flowing that direction, well, flowing this direction, from ground to that point, because the arrow for the current source is there, and what happens is it develops a voltage at the plus terminal of minus IB2 times R3. Now, because this is an op-amp in negative feedback, the plus and minus terminals have to be equal. And this is an ideal op-amp because of non-ideality we're representing by these current sources. So this, for all respects, is an ideal op-amp. So minus is equal to plus, and so that node right here has to also be equal to, in voltage, minus IB2 times R3. If that's the case, then that's going to develop a current across R1, because I've got a voltage here, I've got 0 volts there. That's a voltage drop across R1, so the current in this direction, the arrow that I'm showing here, is going to be minus IB2 R3 divided by that R1. That current cannot go into cannot flow out of the negative terminal, so it's got to flow through R2. So I2 then is going to be equal to this current plus this IB1 current, which is still there, right? So it's IB1 minus this there, and so the voltage out here is then going to be equal to the voltage at this node, which we know is this, plus the voltage drop across R2, which is I2 times R2. And if we take that into account, this is what we get for that output voltage. And so you can see that that output voltage is not necessarily 0, but now you can look and see that we can actually play with this. We've got some things that have, some terms that have negative in front of them. We've got other terms that have positive in front of them. So if that's the case, there's a chance that we can actually cancel this out. And if we pick the correct values of R1, R2, and R3, then we can actually cancel this voltage out. And that's the trick that people use. This is why, if some of you are familiar with electronic circuits and op-amp circuits, and some of you I know are, you've been playing at least as hobbyists or more in this arena, that's why sometimes you see this resistor there. Like if you pick up Horowitz's book, Art of Electronics, you'll see a lot of circuits where, yeah, they've got this, but then they've got this extra resistor there. And I don't know if you knew what that resistor was doing there. What that resistor is doing is canceling out this input bias current. At least that's one of the things that it's doing. So let me now demonstrate the fact that it's doing that by actually analyzing this circuit. Okay, and so let me take two cases too. So let's just take the case, first the simpler case where our input bias current is just average current. There's no offset between the two. IB1 equals IB2. So I'll just say right here, case IOS is equal to 0, which means, in other words, that means that IB1 equals IB2 equals just IB. Okay, and we have no IOS in this case. Okay, so if I take this case right here and I start doing this analysis, well, first thing I'm going to do is take this output voltage here and sort of factor something. So let's call that V0 is now equal to IB. I'm going to stick in IB for the IB1 and IB2, which means I can factor out the IB. So this is now going to be IB times R2 minus R3 times 1 plus R2 over R1. Just a little bit of algebra there. And I think I can fit it. I'm debating whether I have enough space, but I think I do. And so if I want V0 to be equal to 0, that's my goal. Then I'm going to set this equal to 0. And if I do that, I can write R2 is equal to R3 times 1 plus R2 over R1. Okay, and so here I can now solve for the R3. That allows me to set V0 equal to 0 there. And that R3 is then going to be R2 over 1 plus R2 over R1. That's equal to 1 over R1 plus 1 over R2. And if you're good with circuits, you can recognize this as just a parallel combination of R1 and R2, what we often write as R1 parallel with R2. So in the end, what I could say, and I'm going to go to the next page to say this, put a star there, and advance this. So finally I could say, from star to that therefore, if I pick R3 to be equal to R1 in parallel with R2, then even if I have that input bias current, I can make my output voltage go to 0. And that's for the special case where the bias currents are the same going to each node. So that's the case where IOS equals 0. Okay? And so that's the final result that we're getting there. So if I want to cancel out that bias current, I'm just going to select R3 equal to the parallel combination of R1 and R2. So it's these types of circuit tricks that you can develop that really show the value of being able to model the non-idealities in these op-amps. So now I could take an op-amp, an actual op-amp with bias currents, I can apply this, and I'll get very close to an output voltage equal to 0. So I'm not going to get exactly 0 because most op-amps will have a differential current too. They will have a finite IOS. So let's look at that for a second. Let's take the case where our IOS current is not equal to 0. So that means I have some difference between IB1 and IB2, these two things, going into my op-amp. Okay, so I know if IB1 and IB2 were equal, I could cancel it out by choosing R3 equal to R1 and R2. But what happens if I choose R3 equal to R1 and R2, and I have some offset current there? And so let's go ahead and do this. And so let me define this a little bit better too. So in other words, this means that IB1 is now equal to IB plus that offset current, the difference current that we talked about, divided by 2. And IB2 is going to be equal to IB minus that offset current divided by 2. Okay? And so let's go ahead and attack this problem there. So I start with the equation that I got last time. I'll just repeat that equation right here. So I got V out is equal to IB2 times R3 plus R2 times IB1 minus IB2 times R3 divided by R1. Okay, starting out with that same equation, I can now do a little bit of rearrangement here. Well, not rearrangement, but I want to plug in now IB1 and IB2 into this equation. So this now becomes V naught is equal to minus IB times R3 plus IOS divided by 2 times R3. I want to make that look like a 3. Plus R2 times the quantity IB plus IOS over 2. That was the IB1 there. Minus IB times R3 divided by R1 plus IOS over 2 times R3 over R1. Where I've already taken into account that this IOS is negative. That's why I put the positive sign in front of this last one. I'm talking about this right here. And so now let's plug in our solution from last time that at least zeroed out the average current. So R3 is a parallel combination of R1 and R2. So if I chose R3 to be this, then my V naught I can write out as IB times quantity R2 minus what would end up being R2 times R2 over R1 plus R2 minus R1 times R2 over R1 plus I2 plus R2, sorry, plus that difference current IOS divided by 2 times R1 R2 divided by R1 plus R2 plus R2 plus R2 times another R2 divided by R1 plus R2. And you see what I'm doing? I'm just brute forcing this thing right now. But this R2 here, I can just write that as R1 R2 plus R2 R2 divided by R1 plus R2. And so you can see that in this thing I'm going to get some cancellations. And so what's going to cancel here? This is going to cancel with that there. And then this is a minus sign on that. And so this all cancels here. So all of this stuff cancels. I wanted to make those red, and I failed to do that. So let me backtrack a bit and do that. So all of these things cancel right here. Right? So this whole term pretty much just goes away. Right? And so then I end up with this term out here. And so I can expand this term, and this is where the interesting thing happens because things survive here. This ends up being IOS over 2. If you look at that, times 2 times R2 times R1 plus R2 divided by R1 plus R2. And you can see that these things also go away here. Right, I'm going to end up with, let's see, that just goes away right there. And these 2's go away right there. And so finally what you end up with as a final solution, really just brute force algebra is all I did, is V naught times IOS times R2 becomes what I get at the output. And this is much less than IB plus IOS over 2 times R2, right? So I've helped myself quite a bit because I've pretty much eliminated that IB. Remember, IOS is on the order of 10 nanoamperes. IB is on the order of 100 nanoamperes, right? And so this thing here is going to be about 5 nanoamperes there. And so I've helped myself quite a bit by doing this. And so from this, the takeaway is that setting R3 equals R1 in parallel with R2. It doesn't eliminate IOS over 2, or the IOS here, but it still helps. Even if IOS is not equal to 0. Okay? And so all I'm doing is showing you tricks. This is a trick right here to reduce the effect of some of these non-idealities. And if you study practical circuit design, say you start looking at the circuit schematics of certain electronics, which you can now do, understanding all these non-idealities, you can now start to understand why you see some extra elements like this R3 here that you would normally think isn't needed. And they're needed to make the practical circuit work in the face of these non-idealities. Okay? Are we supposed to use both current, I'm looking at the chat, are we supposed to use both current offset and voltage offset when modeling a non-ideal op-amp circuit? Yes, in general, you'll have both a current offset, you'll have a voltage offset, but in this class, what we will do is tell you what the non-idealities are. So we'll tell you that in this problem we have a VOS. In this problem we have an IOS and an IB. Sometimes we'll have both, etc. But in real life you'll have both. And so the problem will become worse. But a lot of times in real life you're really only worried about one of them. Even though you know the other one exists, the other one becomes more important in the specific circuit application that you are focusing on. So I hope that answers your question. Okay, good. All right, so that's it for op-amps and op-amp non-ideality. We spent a good amount of time on this, and I think an appropriate amount of time, because this is a very important topic for anyone learning circuits. But now let's talk about the reasons why these non-idealities happen. And to do that, we have to understand devices. And before we can understand devices, I want to generalize some of the things that you've learned before. And so I want to talk about what I'm going to call generalized circuit elements. And kind of what I mean by these generalized circuit elements, what I'm going to focus on are nonlinear circuit elements. So what we're really generalizing them is to get them away from linearity, which is what you've assumed, I believe, over all your previous courses before this, if you've taken only the equivalent to 16 and that sort of thing. And so let's start with our circuit elements. You know what our elements are. We have resistors, we have capacitors, we have inductors. So let's start with a resistor. And so for a resistor, what do we know about? We know about linear resistors already. And so if I wanted to draw a linear resistor, this is what it would look like. That's our symbol, of course. I can model the current going through it and the voltage, and the current will be related to the voltage by V over R. And because it has such a simple relationship that's relating current and voltage, I can plot my current versus voltage. And what I'm going to get is a straight line. Right? And that straight line is going to have a slope 1 and R. Right? And so that's what we know as a resistor. But a resistor is actually a good deal more general than that, because a resistor doesn't have to be linear. It can be nonlinear too. And in general, it is nonlinear. If I have a nonlinear resistor, then oftentimes I will give it a symbol like this. This is its conventional symbol, where now I'm saying where the plus and minus terminals are. So where I have that big colored area there, dark area there, that's where the negative terminal is. And so in this case, I'll still have a current running through this, still have a voltage going through that, but now the current depends on that voltage by some function f of v. And if I were to draw or graph this, then this can take on all sorts of shapes. So one common shape that we have for one of our devices is like this. This is like a tunnel diode type thing. That's not a device we'll be using, so actually I shouldn't have said that's a common shape, but for people that use tunnel diodes, that's a common shape. And so this is just showing that we have generalized this to something that actually can model more of the actual devices that we're going to be playing with. Okay, so that's one thing. That's an important new element for us. Not really new, it's a resistor, but it's now nonlinear. And I can apply the same principle to our other elements. And so let's take a look at a capacitor, something that you've already played around with, also played around with quite a bit. And so my capacitor symbol is this, of course. And if I put a voltage across this capacitor, then what's going to happen is that's going to induce charges, a positive charge on that plate of the capacitor, a negative charge on that plate of the capacitor. And to model our capacitor, oops, I forgot to title this linear capacitor, so let me do that. Let me move this down just a bit and title this. And so same thing, we can make a plot to describe what this capacitor does. And what this capacitor does in general is it changes, the voltage changes the charge across the plates of the capacitor. And you know that the equation for the relationship between the charge and voltage is Q is equal to C times V. And so in the end, to plot this, I'm just going to plot a straight line like that, and the slope is going to be equal to C. I'll make my little triangle for slope. Right? So that's what we understand as a capacitor now, but again, I want to generalize this to a nonlinear capacitor. And a nonlinear capacitor, we're going to do something similar to what we did above. I'm going to take the capacitor symbol, I'm going to put a big block around it. I'm going to indicate where the negative terminal is. So I have my voltage there, and then on this plate of the capacitor I'll have plus Q. On that plate of the capacitor I'll have minus Q. And now if I wanted to draw a graph that describes what's happening here, that's V, that's still Q. But now Q is going to be some function of V. Okay, let me make it like a G of V, some function of V. And what is that function going to look like? Well, it can look like all sorts of things, and a lot of times it's going to look something like this for us. Okay, but these are just generalities now. I'm taking things that you already know, and I'm allowing them not to be linear. And for those of you that have studied math, and all of you have to some extent, that means that a lot of our linear math theories just go out the door for this. We can't really solve these things very easily the way that we have been in the past. And so we have to find a way back to being able to use the math that we know for linear type systems, even on these nonlinear problems. And so the reason why I'm showing you these nonlinear things is because the transistors, the diodes, all the things that we're going to use, they are actually nonlinear elements. And we will have to deal with this nonlinearity. And so let me do one more thing here, and let me actually not do it, but just say that there is an inductor too. So I'll just say there are nonlinear inductors too. So we also have nonlinear inductors, but they're generally not seen let me qualify this in low to mid frequency. Integrated circuits. Okay, so we won't work with these. In this class. You'll also not see many of them in 140, but in something like 142, where you're looking at very high frequency, you'll start seeing inductors come back in. Okay, so I'm not going to actually do the same thing with inductors there. I'm just going to say that about that. But let's move on to now our first semiconductor device, and that is a diode. So you've probably played around with diodes before. You may even know that they're semiconductor devices. But let's take a look at diodes now. And I guess diodes are an example. These are an example of nonlinear elements. I'll put an S there because actually a diode consists of two of these nonlinear elements. But let's start taking a look at the several types of diodes that we have. So we have several models. All of which represent nonlinear resistors. And I could say in parentheses and nonlinear capacitors. If we want to be very accurate, but we're not going to be that accurate right now. We're just going to do the simple thing here. So let's take a look at the different models that we have for diodes. So the first model for diodes is the ideal diode model. This is something that I suspect you've already played with a bit in previous courses, although I'm not sure anymore. Do you see diodes in your previous courses? 16? I guess there's no way for me to see. Not in the 16, really? Oh, yes, in 16B. Okay. Yeah, so I think this is where the variation in the 16s really comes in right now. Some of you may have seen this, some of you may not have. And so we're going to go into it pretty deep. We're going to go a lot deeper than diodes in this class. So I guess buckle up at this point. This is going to be stuff that maybe a lot of you have not seen before. Not today, but deeper in. We'll get there. But an ideal diode, I think, may be best described by its graph. So if I graph the current versus voltage of an ideal diode, then what this looks like is at any voltage below 0 volts, there's no current. I get 0 current. But then as soon as I hit 0 volts, suddenly I get all the current I need. And so that I could source an infinite amount of current there. And that's why it's an ideal diode. So for an ideal diode, a lot of times you'll give it this symbol. And so where a lot of you, I think, know that triangle with the bar is a symbol for a diode. But if I want to make it an ideal diode, I put a circle around it. And so I'll have that's the voltage. This is the current going through my ideal diode. And so that symbol gives me this transfer function. 0 current for any voltage less than 0, then suddenly lots of current for voltages greater than 0. Okay, so that's an ideal diode model. If anything, those who've seen diodes have seen something like that. Then there's another model for this, which I can call a constant voltage model. And so in the constant voltage diode model, again, I'm going to first explain it or describe it by its plot, IV characteristic. Also, for any voltage less than 0 volts, no current is allowed. But still no current allowed for some very small voltages until you get to a voltage VD0, which is the diode turn-on voltage. I guess I'll just call it the diode on voltage, which is usually from 0.5 to 0.7 volts. But once it hits that, then similar behavior to the ideal. It sources as much current as needed to satisfy whatever circuit it is. And let me write that down, because people get confused by that infinite current line going. What that means is it can source as much current as governed by Kirchhoff's laws, by KCL or KVL. Okay? And this is saying the same thing when it goes straight up like that. And so for this non-ideal, well, this is not as ideal because I'm saying it has a turn-on voltage. It's just not turning on at 0 volts. But for this diode, I can also give it a symbol, and I'll give it the same symbol. I'll give it the same ideal diode symbol here, like that. But now I'm going to put a voltage in series with it to say that you don't really get that turn on until your voltage across this whole thing, so the voltage going into this, that voltage right here, until that is greater than 0 plus this VD naught, you don't get the whole thing turning on in this. And so in the circle, I have an ideal diode, but I put a voltage source in series with that such that in order for this to give the ideal diode characteristic, I have to have a voltage at least as big as VD naught. And so you can see that this circuit gives this characteristic if that ideal diode gave that characteristic. Okay, so that's all I'm doing. I'm just lumping different circuits on top of each other to describe what this is doing right here. Okay, so those are two diode models there, and those are both kind of ideal models, but in actuality, what we'll be playing with are actual diodes. That doesn't mean we will never use these models, the constant voltage and ideal model. In fact, I'll show you what an actual diode is, just for your information, but in the end, we're going to simplify things. If we're good circuit designers, we will simplify things into this model or that model, usually this model right here. So this constant voltage model might be the most important model to us eventually. But right now, let's talk about what a real diode does. A real diode does this. So here's current, and I'm going to make a sort of a lopsided curve like this. This is the voltage axis here. This is my turn-on voltage, what I'll call VD naught. And yes, when I hit VD naught, this thing is going to go up very fast, but it's not going to go like a brick wall. It's not going to be like a step function there. It's going to have some curvature at the bottom. It's going to take a little bit to turn it on here. Right, you get a little bit of current there, and when it gets to this side, it actually does not have 0 current on this side. It actually has a little bit of negative current. Right, you're applying a negative voltage, so the current should go in the opposite direction to this thing. But even beyond this, at a certain voltage out here, it'll start going back up. I should say back. I should start going down with a lot of current there. It could source almost infinite current going down in that direction. This is what a real diode does. And so this is actually a breakdown voltage. Where breakdown obviously is a non-ideal type of thing there. And for the voltage and current that I'm talking about, this is the symbol. And so this is a symbol for an actual diode. I don't have a circle around it or anything like that. I'm just drawing it like that. And that is my actual diode. And so for this actual diode, the equation that models the current going through this involves a lot of physics. So it involves something called IS. IS times the quantity E to that voltage divided by N times VT minus 1. Okay, what's N? What's VT? What's IS? That's something we'll learn about when we start talking about physics, but I'll tell you right now what some of these things are on the next page. Whoops. Not that page yet. Let's go here. And so, why don't I rewrite this equation here? Or why don't I just copy this whole thing here? Actually, why don't I copy the whole darn thing so I can keep everything together for you. Okay, so if that's our actual diode there, then I can define I sub S as the saturation current. That's something that you can actually determine by physical parameters of the actual device. VT is 25 millivolts actually, depending on temperature. That's at room temperature. That's equal to KT over Q. And so maybe in your physics courses you've seen that KT over Q before. If not, we'll talk about that. This is what we call the thermal voltage. And you see it depends on temperature, so I'm giving that value at room temperature. In some cases, people will use 26 millivolts. You'll see some textbooks doing that. N is equal to 1 or 2. And 1 is if you have an integrated circuit diode. That's usually what you get. 2 is what you'll get for discrete diodes. So off-chip diodes. Types of diodes you'll be using in this class. But this is the model then for this diode, and this is the type of transfer function you get for this diode. And so I'm kind of drawing this as this is basically a nonlinear resistor function. Right? I've got I as a function of V here. So I can call this my F of V that I was calling before when I talked about nonlinear resistors. But I should be a little more complete about this and say that diodes are not just a nonlinear resistor. So if I want to talk about a diode, I should say, and I'll write that down what I just said, not only a nonlinear resistor, but also includes nonlinear capacitance. Okay, and so a more exact model would include both of these things. And so let me show you that more exact model. Whoops, what happened here? Okay. So that more exact model would look like this. And so I'm still modeling this thing. Same symbol. I'm putting a voltage across this. I'll get some kind of current. But this thing really equals the combination of a nonlinear resistor and a nonlinear capacitor. And so I could think of this as my total current I. This is going to dictate a current I sub D, where I sub D is going to be equal to that equation that I just showed. That's like F of V is going to be equal to I sub S times E to the V over NVT minus 1. But on this side, right, I put a voltage across this whole thing. That voltage is also across that resistor on that side there. But if I put a voltage here, I'm also going to develop a charge plus Q and minus Q there, where these charge Q, I can give another function of voltage V. And after we learn physics, you're going to see that this is equal to Q, which is the unit charge, times what we'll call N sub A times N sub D, divided by N sub A plus N sub D. These are going to be dopant concentrations in our actual semiconductor, times A, a cross-sectional area, times WD naught, which is going to be a depletion region width. And I'm running out of space, so I'm going to cheat a little bit and move this way. And then all this times square root 1 plus V sub r, which is the reverse of R voltage, divided by some potential phi j, where I'll just say V sub r is equal to minus V. So this is actually how to properly model a diode. None of this you understand yet. I know this, so don't worry. If this is snowing you, and then that's not a big problem. Interesting. Is everyone hearing me okay right now? Okay, that's interesting because I've got a big exclamation point next to my audio thing on Zoom, but I guess that means nothing, so I'll keep going. All right, so that's great. So that's our diode model there. So now what we want to do is start talking about semiconductors. Okay, and so this is now going to be a very important part of what you learn in this class. It's actually a cool part of what you learn in this class, and I hope that these lectures that we're about to go in will help you to be comfortable about taking a course like 130 and other physics courses that teach you really the details of what's really going on inside the devices that you're using, all those ICs and things that you got in your lab kit. We're now going to talk about what's really inside of those things. And so to understand that, we have to understand semiconductors, our next topic. But to better understand semiconductors, which means to better understand the physical operation of diodes and later transistors, we need to understand semiconductors, but it's best to describe them, I think, in the context of other materials like conductors and insulators that you already know about to some degree. At least you can hold them in your hand and that sort of thing. How much of the physics you've learned depends on your background, but we'll talk about that. And so these are materials, of course. They're made up of atoms. I think we all know that. In solids, the atoms bond together in a regular lattice. Oftentimes they're a regular lattice, not all the time. Sometimes they're not arranged in a lattice but are amorphous, like glass, for example, is amorphous. But silicon and a lot of the metals that we'll talk about are in a regular lattice. The atoms in the lattice are happiest in their lowest energy state. So they're like you and me, right? We're often happiest when we're at rest, right? We're sitting in our recliner doing nothing. Well, that might not be true for all of us, but that's when we have our lowest energy state, and everything wants to get to a lowest energy state. And for atoms, hopefully you've learned this in your chemistry or physics classes, they're happiest when their orbitals are filled. Okay, and so we can go to the periodic table, but I guess before I do this, let's talk about conductors first, and let me talk about what I mean by those orbitals and that sort of thing. So let's take example of a conductor. So a conductor is a close-packed set of atoms in a lattice in a cloud of electrons. And so what do I mean by this cloud of electrons? Let's take, for example, sodium. Sodium is a metal. It's an alkali metal, which maybe you've learned in the past. That means it has one valence electron. And so in this case, what we're talking about is a situation where we have a nucleus. Let me go ahead and draw this here. So say I have a nucleus. I've got protons and neutrons that create my nucleus. And if it's sodium, that's 11 protons. Right? But this nucleus, of course, if I have 11 protons, then to keep this all neutral, I've got to have 11 electrons around this. Now, I'm giving you a very simplified picture of this right now. If you're a physicist, you're going to laugh a bit because, you know, you can go to much deeper stuff where you could start talking about quantum levels and this sort of thing. I'm kind of talking about quantum levels because I'm talking about orbitals and that sort. But, you know, I'm not going to do a complete job of this. I'm just want to get across as much as I need to help you understand semiconductors right now. But around this nucleus, I'm going to have orbitals of electrons. And each of these orbitals, from quantum physics, right, will want a certain number of electrons around that. So this first orbital, you're going to have 2 electrons. Right, so maybe I have 2 electrons, and electrons I'll call E minus. Right, the second orbital on this, you're going to have 8. 1, 2, 3, 4, 5, 6, 7, 8 electrons to be happiest. And then finally, in the last orbital, You also, the last orbital in sodium, at least you'd like to have 8. But in sodium, remember, we have 11 protons. There's 2 in there. There's 8 out there. That's 10 right there. And so all I have is 1 electron. I have 1 lone electron. Let me put it on the other side. Okay. That's easier to redraw. So there's my electron. And that's 1 electron in what's called the valence shell. Valence is kind of the same term as outer shell, right? So I've got this 1 electron in the valence shell. And if you have just 1 electron in your valence shell, this is not a happy atom because its orbital is not filled, right? This is an orbital. The shell is an orbital, right? And so that orbital is not filled. It wants 8 electrons there. And so what happens in our sodium metal, what sodium actually looks like is something like this. Interesting. Somehow my atoms got distorted. There's supposed to be circles there. And let me see if I can fix that real quick here. Doesn't need to be fixed, but if I could fix it, I will. Text options. Here, do not autofit. And now I'm just gonna, there we go. Those look more like atoms, and now I'm gonna make them a bit bigger again. There we are. Okay, so this now is my set of sodium atoms in here. And so let me, well, let me make that a little bit smaller here because I'm going to need some space. Like that. So these are all sodium atoms, and I guess I will go ahead and label them sodium atoms. And so on and so forth. And this is what the atoms look like in a lattice. Now, when you look at these atoms, they're all very happy, except each of them has this extra electron. Right? This one has got an extra electron right here. And the sodium atom is not happy if it has that extra electron. None of these sodium atoms are happy with their extra electrons. And so what happens in this lattice here is that each of these extra electrons, because the sodiums are not happy with them, they don't fill their outer shell, they let the electrons go. And so what really happens is this electron now is free to move around. All these electrons are now free to move around this whole thing. And so that's why we call it, in a metal, you have a cloud of free electrons that are just moving around at will in that metal. Okay, and then when you actually apply electric field across this, let me come in with a voltage, and so maybe I'll put some voltage V sub D there. That's that, not quite a diode we're talking about yet, but I'll call it V sub D anyway. Say I put a V sub D that has a plus on the left and a minus on the right. Well, if that's the case, then my electric field is going to be in this direction. And if I have electric field in that direction, then the electrons are going to want to move in the opposite direction. So by the action of that electric field, these electrons are no longer going to move around randomly in this cloud anymore. They're all just going to be directed now by the electric field to head in the direction of the electric field. And the reality is they're not going in such a straight line that I'm showing there. They're bouncing off of atoms, or at least bouncing off of shells, and then sort of taking a tortuous path toward the left side there. But this is what happens in a conductor. Okay, and so I guess we're kind of out of time here, but the last thing I want to do is just show you where sodium is on your favorite thing, which is the periodic table. And so I don't know how long it's been since you've looked at a periodic table. The reason why I'm doing this, because later on we'll take a look at silicon, aluminum, all these other elements that we'll care about are right here, but sodium is right here. So this is what I've been talking about. Talking about sodium. Sodium is not a typical semiconductor element. I think here I have to go a little thicker. But it served as a good example of what a metal will do. A metal basically has an electron or a set of electrons in an unfilled orbital that just wants to leave that sodium. And it can do that once you get that sodium and put it in a lattice with other sodiums. Right? So when you create a solid, suddenly you create a mechanism for these electrons to move around, and you end up with what we call an electron cloud in this case. Okay, next thing we'll talk about next time is insulators. That'll be this, but we are out of time, so I will see you next time, which again will be Monday very early morning, maybe 8 o'clock, maybe 9 o'clock. You'll see it by the Zoom link that I give you. I'm going to try to make it 9 o'clock, but if I can't, it may unfortunately have to be 8 o'clock, but it will be recorded. Okay? That's it for today, though. Everyone have a nice weekend, and I hope I see many of you on Monday.